Okay, so today we're going to move on to look at pressure. So we've looked at concentration changes so far, and that if we add something, the system responds to minimize the change by using it up. If we remove something, the system responds to minimize the change by making more of it, or to replace whatever was lost. So we're going to move on today to look at if we changed the pressure. Now I want you to kind of visualize this. It's quite easier to understand if you visualize it. If we've got our system like in a balloon and we're kind of squeezing it to increase the pressure, or letting go of it to kind of relax it and decrease the pressure. Really importantly, pressure changes are only going to work in systems that involve gases, because this all relies on the moles of gas, or the number of particles of gaseous particles that we can make or get rid of to change the pressure. So if there's only solids and liquids, we can't really change the pressure, because if we've got a container here and we've just got solid sitting at the bottom, or some liquid floating around, think back to your Year 9 matter unit. If I make more liquid, more solid, it's got nothing to do with the pressure, because it's not bouncing off of the walls of this container, which is what pressure is. It's the bouncing off of those particles from each other and off of the walls of the container. Okay, so if I increase the pressure, so we've got two options here. We increase the pressure or we decrease the pressure. Now what sort of changes could we have here? So if we increase the pressure, now how might we do that? We decrease the volume of the container. So it's like squeezing our balloon into a smaller space, or pushing the syringe to the end so that there's a smaller volume at the end of the syringe. Okay, so the smaller the volume, the greater the pressure. Okay, so we increase the pressure. What's going to happen? Our system responds to minimize the change by shifting to the side of equilibrium that has the smaller number of particles in the gaseous phase. So it's really important that it's about the particles in the gaseous phase. So we don't care about solid, liquid, aqueous when it comes down to changing the pressure. So I've got an example here that we can have a look at. So I've got this equilibrium of nitrogen gas and hydrogen gas reacting in equilibrium to form 2 moles of NH3 gas particles. Okay, so we've got a whole lot of gas in this one here. Now if we have a look on the reactant side, how many moles of gaseous products do I have? So I've got 3 moles of hydrogen. Nothing in front of that nitrogen means that it's 1. So I've got 4 moles of gas on this side, of gas only. So really important with pressure, we're always referring to the fact it's of gas. On this side, I've only got 2 moles of gas. Okay, so which side produces the most moles of gas? Well, the reactant side in this case. So this is specific to each reaction. So here's my jar that I've got here with a lid on it that's just not showing. I've got my 2 moles of NH3, so I've got 2 there, 2 here. I've got 3 moles of hydrogen, 1, 2, 3, 1, 2, 3. So obviously this is showing like twice this, but in real life this would be in the like trillions of molecules, but they're in this ratio in equilibrium. And nitrogen, 1 and 1. Okay, so I'm sitting here in the container. Now if I increase the pressure, so I'm going to squeeze it into a tighter space here, I'm going to have higher pressure, and I'm going to favor the reaction direction that makes the smaller number of particles of gas. So in this case, it's going to favor the forwards direction, because I'm going to only make 2 moles of gas versus making 4 moles of gas. Now the less gaseous particles that I have floating around and bouncing off the walls here, the lower the pressure. So my system is responding to this increase in pressure by lowering the pressure. And it's doing this by making less moles of gas particles to bounce off of those walls. So in this case, the reaction is going to favor the forwards direction, making more product in order to decrease that pressure. On the other hand, so here we go, there are only 2 moles of product and 4 moles of reactants in the system at equilibrium. Now when you do NCA answers, you have to refer to the number of moles of gas on both sides. So you need to say there is this many moles of gas on the reactant side and this many moles of gas on the product side. You can't get an excellence if you don't do that. So therefore, like we said, increasing the pressure, squashing it into a smaller space, will cause the equilibrium to shift to the right, favoring the forwards direction, because this produces the least moles of gas, which will in turn reduce the pressure of the system, and therefore following Le Chatelier's principle, and that it will minimize the change that has been applied to the system. Therefore, so remember we need to link this back to the actual example, the concentration of NH3 would increase until equilibrium is re-established and the system has returned to its equilibrium state, where the rate of the forwards and the rate of the back has returned to being equal. Okay, so the alternative to increasing the pressure would obviously be to decrease the pressure, like on this side here. Now the way we can decrease the pressure is to give the reaction more space or greater volume. So if you pull the syringe back, you're increasing the size inside of the syringe. Or if you stop squeezing the balloon, it's going to have more space for it to move around. So in this case, if you decrease the pressure, the system responds to minimize the change, and it's going to do this by favoring the reaction direction that makes more moles of gas in order to increase the pressure again, to return to its equilibrium state. So, remember I said in your NCA answer, you have to refer to the number of moles of gas on both sides. So again, I've put a decrease in pressure will cause the equilibrium to shift to the left or backwards, however you want to say it. Because there's a greater number of moles of gas. You have to say of gas. You can't look at any solids or liquids. There's 4 on that side versus the products, which have 2. So I have included here how many moles of gas is there on either side, being really specific, 4 versus 2. This will result in an increase in the pressure of the system, which will minimize the effects of that change, which was to decrease the pressure, which in this case, linking to my example, would increase the concentration of nitrogen and hydrogen and decrease the concentration of my product. Okay, here's another one that we can look at here. How many moles of gas? So when you see it's to do with pressure, we want to look at how many moles of gas. That's the first thing I want to do. So I've got 1 mole of hydrogen and 1 mole of chlorine. So there is 2 moles of gas on the reactant side. On the product side, there's 2 moles of gas. Okay, so I've got 2 and I've got 2. So if I decrease the pressure, my system would respond to increase the pressure or to favor the side that makes more moles of gas, which, as you can probably see by now, isn't going to work here because it's 2 on one side and 2 on the other. So which one would be favored? Okay, so none. This isn't going to work. Pressure changes have no effect on an equilibrium that has either no gas or has the same moles of gas on either side. There is going to be no change. Really importantly, just like with concentration, pressure changes have no impact on the value of Kc. Keyword, the ratio of reactants to products will return to normal. So yes, we'll have more reactant and more product, or less reactant and less product, but the ratio of them will remain the same. So let's have a look at this one here. What will be the colour of the mixture of gases when the volume of the container is decreased? Yes, sorry, I couldn't see that 2 there. So we've got 2 NO2 going to 1 N2O over here. Okay, so let's have a look at this example here. So you can't quite see it, but we've got 2 NO2 gas goes to 1 N2O for dinitrogen tetroxide. So I've got a brown gas here as a reactant, and I've got a colourless gas here as a product. So because it's talking about gases here, I'm looking at volume, I'm starting to think pressure changes. I'm going to first look at the moles of gas. So on the reactant side, I've got 2 moles of gas versus 1 mole of gas on the product side. So the container is decreased. So what is that meaning for pressure? I'm decreasing the container size. So I'm squeezing it into a tighter space. I am increasing the pressure as the volume has been decreased. Okay, so that's the first step we need to identify. Next thing is our generic statement. System responds to minimize the change. And it's going to do this by decreasing the pressure again. And it does this by favoring the reaction direction that produces more moles of gas, because I'm trying to What are you doing?
Pizza.
Where are you doing to that?
Oh, I just myself.
Because I could hear it in my thing. That again.
Are you firing?
Hmm?
Are you firing?
I'm recording right now. Right now. So I'll just have to cut all this out. Okay, so let's have a look at this example here. So I've got, you can't quite see it here, but 2 moles of NO2 gas on the reactant side, and I've got 1 mole of my dinitrogen tetroxide on the product side. So what's going on here? They're asking me to explain the color, so that's what I need to link back to, of the mixture of the gases when the volume of the container is decreased. So if I decrease the volume, so think about the balloon example, we're going to squeeze it into a smaller volume. That is going to lead to an increase in pressure. Remember our generic statement here, the system responds to minimize the change. Which in this case will be to decrease the pressure, because I've just applied a change, which is an increase in pressure. System's going to respond to decrease that pressure again. Okay, it's going to do this now by favoring the reaction direction that makes the least moles of gas. Okay, because I'm trying to decrease the pressure, I need less gaseous particles bouncing around my container. So let's have a look here. Remember, I need to refer to the specific example. So here, reactants have 2 moles of gas, really importantly we say of gas, versus products 1 mole of gas. Therefore, we're going to favour the forward direction. The forward direction is favoured, which will appear lighter brown. So remember, it's not going to go colourless because there is still some of this brown gas present, just a little less as it's turning into my dinitrogen tetroxide, which is colourless, to try and restore equilibrium. So it's going to go a lighter brown, but only until equilibrium is re-established. Okay, that's really bad to read, but I've summarized it very nicely for you over here. So, like I've said here, very importantly, you need to actually link your explanation to the actual question throughout, including the exact number of moles of gaseous reactants versus products. So some key words there. So we need the exact number, like 4 versus 2, 2 versus 1. Gaseous reactants or product. So we can't just say there's 4 moles of product, 2 moles of reactant. It has to be gaseous products and gaseous reactants. So for example, I increase the pressure of my system, maybe by decreasing the volume of the container. The system responds to minimize the change by decreasing the pressure again. So I just increase the pressure, my system wants to respond to decrease it again. It does this by favoring the reaction direction that produces the least moles of gaseous particles. So remember, this is where we'll have to put in the reactant side have 4 moles of gas, the product side have 2 moles of gas, therefore the forward direction is favoured. So it's specific to the actual equilibrium that you've got. On the other hand, if I decrease the pressure, maybe by giving it more space to occur, so bigger volume, system responds to minimize the change by increasing the pressure again. It does this by favouring the reaction direction that makes the most moles of gaseous particles. Again, link in here. There's 4 moles of gaseous particles on the reactant side versus 2 on the product side. Therefore, the backwards direction would be favoured, which would make more reactants. Okay, so I'd always link it back to the example. This all continues until equilibrium is re-established. Again, no change in Kc. Okay, so let's have a look at this example together. Ugh. Why does my life hate me?